Hello, everybody. Welcome back. Today we're going to be looking at Unit 5.1. We're starting a new unit today. And 5.1 is all about reaction rates. So let's get started. So for those of you that have watched my videos before, you always know that I like to start a unit with a little factoid, and I think this is really interesting that this person was given the Nobel Prize for finding the cure for cancer, and that is overly optimistic, as I don't think that has been discovered yet. Anyway, I just thought that was interesting. And that image that you're seeing in front of you, that is a cancerous cell. That is not how a healthy cell is supposed to look. So, Unit 5 is called Kinetics. And let's talk about what that means. Please don't get this mixed up with the word kinematics, which is a physics term. Although they are related, kinetics has to do with reaction speeds. How fast or how slow does a chemical reaction take place? And we've talked a little bit before about spontaneous reactions, ones that occur on their own without any outside intervention, but we haven't ever talked about how slow or how fast they are. So how do you measure the speed of a reaction? I mean, if you think about how do you measure the speed of a car, typically we express speeds of a car in miles per hour or kilometers per hour, a unit of length per time. So how do you apply sort of that same concept to a chemical reaction? And the way that you do that is by measuring the change in concentration, so the change in molarity of a reactant or a product, either way, per some unit of time. That's how you measure how fast or how slow a chemical reaction is. Okay, and sometimes you will see this sort of indication here, like that, which just means, remember, brackets mean molarity, change in molarity. Okay, again, that could be change of a reactant or it could be change of a product per a change in time. So let's look at an example. Okay, so we have this simple synthesis reaction, the synthesis of ammonia. And as the reaction progresses, we are going to see the concentration of hydrogen, which is one of the reactants, we're going to see it decreasing over time. Okay. And that's the graph that we're seeing in front of us. Time is on the X, concentration is on the Y. Reactants are consumed, so the concentration should be decreasing. Now look at the curve for nitrogen, which is the other reactant. It's a reactant, so it is also decreasing over time, but I want you to notice that it seems to be decreasing not quite as fast as the hydrogen is. It's not being consumed as fast as the hydrogen. And that should make sense to you. Look up at the equation. Nitrogen has a coefficient of 1, hydrogen has a coefficient of 3. Hydrogen will be consumed 3 times faster than the nitrogen will be consumed. Or we could say this another way. Nitrogen's concentration will be decreasing 1/3 as fast as the hydrogen is decreasing. So they are both being consumed, they're both decreasing over time, but the hydrogen is decreasing quicker because of that coefficient. So rates are dependent upon those ratios. What would be happening to the product? Ammonia, since it's a product, is being created, produced. It is increasing over time. Okay, and if you wanted to get technical about this, ammonia is increasing twice as fast as nitrogen is decreasing. Okay, again, it's just a relation of those molar ratios, those coefficients. Okay, so you're going to see questions in multiple choice and free response, both using numbers that you can usually do in your head. And it's all just to do with those molar ratios. So it says if the rate of disappearance of nitrogen is 0.025 molarity per second. Okay, let me just pause there for a moment. Look at those units. Those are the kinds of units you will see for rates of reaction. Molarity per second. Okay, concentration per time. So if the rate of disappearance of nitrogen is 0.025 molar per second, what is the rate of disappearance of hydrogen? Let's take it one question at a time. Change color here. Okay. 0.025, and that's molarity per second. And guys, all I have to do is use those molar ratios. That given number, 0.025, corresponds to nitrogen. And they're asking me about hydrogen. These are in a 1:3 ratio. So the disappearance of hydrogen would be 0.075 molarity per second. It's just a factor of those coefficients. They also ask us what is the rate of appearance of ammonia, and I'm going to do the same exact process. Take the rate that I was given, and I'm going to use those ratios, 1:2. So the the rate of appearance of my product is going to be 0.050 molarity per second. And those are numbers you could work with in your head. So that is something that could very easily be in multiple choice. Okay, just a little bit of vocabulary here. Those of you that are familiar with calculus are going to see some connections between kinetics and calculus. I'm not going to point out those connections because this is not a calculus-based course, but you will see some connections, and you might see it here with this graph. So just a little bit of vocabulary. If ever you see the term average rate, okay, that just means the change in concentration over a long period of time. That's not something we're typically going to be looking at. We will more often be looking at what's called an instantaneous rate. And if we were in a math class, we would pick a point on that line where I want to know what the rate is. We would find the slope of the line tangent to that curve. We're not going to use that method, but if we were in a math class, that's what we would do. Let me finish off this subunit by just saying some of the factors that can affect how fast or slow a reaction can go. Okay, reactant concentration. All right, and we're going to talk more about this later on in this unit, but reactions are a factor or dependent upon how many collisions there are between the reactant particles. The more collisions there are, the faster the rate will be. If I were to increase the concentration of a reactant, okay, it's like crowding more people into a room. The people are going to bump into each other more if there's more people in there. The more reactant there is, the more collisions, the greater the speed will be. Same thing happens if you increase the temperature of a reaction. Think about what happens when you raise the temperature of anything. you cause the particles to move faster, to have more energy content, again, there are going to be more collisions, and so the reaction rate will go up if you raise the temperature. Finally, if you increase the surface area, think of a sugar cube versus granulated sugar, like ground up powdered sugar, okay? Ground up granulated sugar has a greater surface area than a sugar cube. More surface area, more collisions, greater speed of reaction. Okay, catalysts, if you'll remember from Chem 1, catalysts are also things that speed up the rate of a reaction. They make it go faster. They make that happen for a slightly different reason, and we're going to address that in a totally separate subunit. So we'll talk about catalysts individually. So let's finish off with just an example problem here. And if you want to pause the video, you can and try it. Otherwise, I'm going to talk through it. It says 2 samples of magnesium solid of equal mass were placed in equal amounts of hydrochloric acid contained in 2 separate reaction vessels. Particle representation of the mixing of magnesium and hydrochloric acid in the 2 reaction vessels are shown in Figure 1 and Figure 2. Water molecules are not included. Which of the reactions will initially proceed faster and why? Guys, if you look at these figures, really the only difference here is that the magnesium in the top figure is in a solid block, and in the bottom figure, it's sort of ground up. It's kind of like the top is the sugar cube and the bottom figure is granulated sugar. Okay, so think about that for a second. That's going to affect surface area. Okay, if you looked at your answer choices, I'm hoping that you realize that the answer C is the correct answer. Figure 2 is going to proceed at a faster rate because that magnesium simply has a greater surface area. There's more atoms exposed to the acid. It's not going to be letter A because the concentration is the same amount of magnesium. It's not going to be answer choice B. Again, we were told they were the same masses. And then D is not correct because it's the exact opposite. Figure 2 has a greater surface area than Figure 1. So that's just an example of a type of question you could see. So that is it for 5.1. And I hope that you have learned a little something today, and I look forward to seeing you next time.